activity
طب
itself.
اعمله تاني، اخرج وادخل تاني، انا عندي دخل من الموبايل.
صوت طلع من كيفك الله. So, Dr. Hussein, the floor is yours to tell us a little bit about the activity and about Professor Fateh.
بسم الله الرحمن الرحيم.
Hussein himself, of course, I mean, I should introduce him. Dr. Hussein was a very senior person in up to being the minister for this ministry, and we are very lucky in have him after he retired from that position, that very senior position, to become here the Secretary General of the Arab Water Council during his time. Really, he did a great job, and together with Dr. Mahmoud Abu Zaid. And I think all of you who are related to the region and the Arab region, you know Professor Hussein. He's really also, in addition to those very high administrative positions, he himself is a very senior person in the area of water in the region and in Egypt and globally. So Hussein, the floor is yours.
Bismillah ar-Rahman ar-Rahim. Thank you very much, Professor Abdin, and let me say His Excellency Dr. Abu Dr. Waid, I don't here with us today, and distinguished guests, colleagues, friends. It's more than pleasure to welcome you all to the second section of our webinar today, titled with How Climate Change Impacts Water Scarcity in the Nile and over the Mediterranean. I believe today's discussion is both timely and critical as we witness the escalating impacts of climate change across our countries, shared river basins, and regional water bodies. In fact, the Nile and the Mediterranean have been since ages cradles of civilization, providing vital water resources for centuries. However, with one set of climate change, these historically water systems are now under severe stress, increasing the temperature, shifting rainfall patterns, and extreme weather events, droughts and floods are increasing water scarcity, threatening livelihoods, agricultural security, and even ecosystem and the socio-political stability of our nations and our region. So today we gather to explore how climate change not only affects the individual countries, but also how it impacts entire river basins that cross multiple borders. Our water systems means that actions taken in one region can have far-reaching consequences downstreams. And these regional challenges require collective responses, fostering cooperation and sustainable management and shared solutions. So we are fortunate today to have with us esteemed Professor Speaker, Professor Dr. Faleh Al-Tahir.
Okay.
Yes, and to Dr. Al-Tahir will share his insights on the physical mechanisms driving these changes and the projected impacts on water availability across the Nile and the Mediterranean regions. And this session also, we aim to deepen our understanding of the regional impacts of climate change on water, means in water security, food security, and peace security even. And explore adaptive strategies that can help us to build resilience. I encourage all of you to engage actively in this discussion and share your perspective on how we can collaboratively address these pressing challenges and how we can empower communities to prevent and to mitigate and to recover from climate related risks. So with this, I would like to thank you all, and I now invite Professor El-Fatih to take the stage and lead us into main presentation. Professor El-Fatih. Yeah.
Thank you very much, Dr. Hussein Al-Atfi, for this introduction and the kind words. And today we continue our set of seminars from yesterday. And yesterday we talked about Arabia, we talked about water and heat in Arabia. And very happy to be with this group, the Arab Water Council. The Arab Water Council is about the whole Arab world. So yesterday we talked about Arabia. Today I would like to talk about the Nile Basin, but also the Mediterranean. And hopefully by talking about these three different regions, we cover the whole region of relevant to this organization. And I decided in preparing for this lecture that I will start by talking about the Mediterranean. First, I will talk about the Mediterranean, and then we conclude by the discussions about the Nile. And so the pictures that you see here are basically on the left, pictures for changes in precipitation. You see this green region in
Let's stop sharing.
أو خليها القرفة دي بتنزل فيه وخلاص. بحطها
Okay. So I'm sorry for the interruption. So we are going to be talking first about the Mediterranean region, and then we talk about the Nile. The picture you see on the left here is a picture that shows how the changes in rainfall are going to impact the whole Mediterranean region. And you see, as a result of climate change, precipitation is going to increase in many parts of the world, except the area around the Mediterranean, however, would be impacted negatively. And we are going to discuss the reasons for that. The picture on the right, however, is one of my favorite pictures when I give lectures. And I'm going to share with you what this picture is about. It's not a picture, it's a drawing. This is a drawing by David Roberts, who visited Cairo in 1850. And I have a lot of, interest in things that happened in the 19th century. So this is before the times of the iPhones and so on. So he went and visited, this is a drawing of the rhodanilometer. And so he went there and he saw those two gentlemen, they go down and you have the gauge, and that's how they monitor the level of water. And so it's a very nice picture. I have it at the cover of one of my books, and I'm going to talk about it later. So again, as I discussed yesterday, this what I call the logo of climate change, the changing concentration of CO2 out of the coast of Hawaii. And I'm going to talk today about how that's going to impact the Mediterranean basin. And you see here, this is a picture for the Mediterranean basin. And the Mediterranean is a region of critical importance. It's a transition zone, as you see on the left. It's a transition zone between the dry subtropics of the Sahara and the wet mid-latitudes. You see more rainfall in Europe, no rainfall in the Sahara. The Mediterranean is a transition zone, and those transition zones are usually zones that get impacted significantly with climate change. Generally, limited and variable precipitation concentrated during cold season. I remember till now what I learned in geography at high school in Sudan. مناخ البحر الأبيض المتوسط حار جاف صيفا دافئ ممطر شتاء. So this is ممطر شتاء. It rains during winter, and and I was wondering, even winter is called dafi mumtir, dafi. We see that, but that's an European perspective. For us here in the region, the Mediterranean in winter is not dafi. It's a little bit cold, and you see here in this picture, I think in this picture here, that the forecasts for the Mediterranean are in general relatively bleak. Climate models are projecting severe reduction in precipitation over the Mediterranean. It's the worst among all land regions, particularly pronounced in the southern Mediterranean during the winter season. You see here on the right, this is different land regions, and the Mediterranean is shown here in red. And that red Mediterranean point showed that P minus E, which is hydrology, that's how we measure, how much water becomes available. The difference between precipitation and evaporation is going to decline by 25%. And that's worse than any other land region. And so the Mediterranean, that's why we call it a hot spot for climate change. It's a hot spot for climate change because of the significant differences that are going to be impacting the water availability. So there are important implications for water availability in that region. So the questions that we try to address, I'm going to try to address in this presentation. And I think we are having a delay, a little bit of a delay here, is what drives the projected future Mediterranean winter precipitation decline? And what explains this uncertainty? So why the Mediterranean a hotspot? Just like yesterday, in my presentation, I tried to explain why extreme storms will happen in Arabia. So why did the Mediterranean projected to be really a hotspot with significant drying? And how do future projections, can we translate those future projections into water availability at regional scale? What's going to happen to water in this region as a result of that climate change projection? So the long-term projections are presented here, and you see on the left, the bottom figure here, significant decline in precipitation that's covering the whole Mediterranean basin. And the dots you see in the figure are indicative of the fact that the different climate models agree on projecting that. You see, when we talk about climate models, there are like 40 models that are being run in like centers in Europe and North America, in Asia and Japan and China. So we don't rely only on a single model. So when you have dots here, these dots indicate that the models are agreeing that there's going to be significant drying, which makes us more confident about that. The other thing is that these declines, as you see on the right, are consistent with what has been observed. For this is the observations 1950 to 2018, and you see that around the Mediterranean in brown, indicating that there are already declines in rainfall that have been observed there. So what the models are projecting and what the early observations are showing are consistent together. So, however, the mechanisms explaining those changes is not very well understood, and that's what I'm going to discuss with you today. So there have been findings that there would be a low-level circulation trends. Mainly the area around the Mediterranean projected by the model to have high pressure. Usually regions of high pressure are not the regions where you see rainfall occurring. High surface pressure, just in the basic fluid dynamics and in hydraulics, if you have a high pressure in an area, the flow of water will be away from that area. It will not be towards that. If you have a low pressure, then the flow of air or the flow of water in fluid mechanics would be towards that area. So the Mediterranean is projected to have high pressure, and that increase in sea level pressure is associated with changes in precipitation that are negative. These are the different models, and you see that the models are projecting declines in precipitation. So the next step then is, why do we see a high pressure over the Mediterranean? And the reason for that is, I'm going to explain, has to do with the large scale atmospheric dynamics. And there is more details on that than I would go through, but in general, there will be an enhanced latitudinal temperature gradient in the upper troposphere. The upper troposphere is the region of the atmosphere where you usually have the airplanes fly in that range. It's about 8 to 10 kilometers in elevation. So because of this change in the latitudinal temperature gradient, the zonal jet, the jet is the area of concentrated flux of air in the upper troposphere, will be stronger. And associated with that, there would be changes in what's called the stationary waves. The stationary waves are the waves that are shaping the climate due to the fact that the topography, the large scale topography that we have. And so those shifts in the zonal shifts in the stationary waves happen to occur such that the Mediterranean, which is shown here, would result in a high pressure around it. So coming from the troposphere, we expect that the surface pressure around the Mediterranean will increase. The other dimension of this is looking from the surface up. The surface, or because the Mediterranean is a water body surrounded by land regions, land heats faster than water. So as a result of climate change, the Mediterranean would have a relative cooling compared to the surroundings. It will not warm as much as the surrounding area. And so that cooling would be responsible also for inducing a high pressure next to the surface. So the combination of the high pressure coming from the troposphere and the difference in temperature between land and water drives the circulation of this type that I'm showing here, this circulation associated with the high pressure. The circulation on the western part of the Mediterranean would drive air from the Sahara Desert into Morocco and Spain. You see that here in these winds here. The wind would drive the circulation that way. And over Turkey, it will drive the circulation from Europe down towards the Mediterranean. As I'm going to show in a second, those circulation changes, basically, and you see them here, those circulation changes will tend to reduce the precipitation over Morocco and Spain, and would reduce the precipitation over southwestern Turkey. And so those are the two areas that are most impacted by the declines of precipitation over the Mediterranean. You would expect to see things in southwestern Turkey, in the eastern Mediterranean, in places like Lebanon and Syria, coastal Syria, and so on. And you would expect to see significant changes in Morocco and also in Spain. So because of that, the physical mechanism that explains this wintertime precipitation change over the Mediterranean is a combination of the large-scale dynamics in the troposphere and also the surface forcing. And it explains the pattern and the physics behind the precipitation response. So the circulation plus precipitation trends rooted in this robust physical mechanism would mean high confidence in our project. So how do we translate these projections at local scales? The approach that we took to translate them into local scales involved using regional climate models. We have a model that we developed at MIT. I talked about it briefly yesterday. It's called the MIT Regional Climate Model. What this model allows us is to be able to simulate precipitation at resolutions of about 12 kilometers. And it allows us also to entertain the use of different large-scale climate models at boundary conditions. And so you see here, using that model, we were able to simulate the changes in precipitation around Morocco in December, January, February, March, April, May. And we do that simulations for two scenarios. RCP 4.5, if you remember from yesterday, is climate change with mitigation. RCP 8.5 is climate change without mitigation. And you could see how under climate change without mitigation, we are projecting significant decline in precipitation over Morocco, up to 40% decline in precipitation. That's not a pleasant projection, and that has to be significant adaptation for it. So this is consistent with what the GCMs are saying. This is consistent with what CMF5s are saying. Under the scenario where you have RCP 4.5, which is some mitigation, climate change with mitigation, you see that the decline in precipitation is not as much, smaller, in the order of 20 to 30%. So in order to translate that into water availability, if you are familiar with the use of water in Morocco, it's mostly coming from this river discharge, and that the snow is a major component of the water cycle. This is a picture here of Morocco out of space, and you could see when you look at Morocco out of space, you could see the snow in the Atlas Mountains. So basically, in winter, the precipitation occurred in these mountains in the form of snow, and then it melts and it supplies the water to the rivers. So if you want to project what's going to happen to the water availability, you have to do modeling of the snow, and you have to take that into consideration. And that's something we did in this study, and we were able to project that looking ahead, there will be 5 to 15% decline in the runoff coefficients, how much basically the precipitation, how much of it is remained on the surface. And there is also significant change in the relative humidity. And if you put all these together, the relative humidity is important because the sublimation of the snow, the loss of snow is function of how dry the air. So if you put these together, we are projecting in the order of 30 to 60% declines in the river flow. And so here you see an example, a specific example where these changes in precipitation over the Mediterranean could have really significant impact on the water availability in a country that needs that water, in this case is Morocco. We also have looked at the Eastern Mediterranean and the Syria, Lebanon area, and there are also significant declines in precipitation there and availability of water. So in summary, for this work on the Mediterranean, we propose a comprehensive physical explanation for this wintertime Mediterranean drying. It's a result of a combination of the large-scale circulation change and the regional circulation response to the sea surface temperature cooling. Is consistent with observations, theory, and model simulations. Downscaled these climate projections over Morocco to a high resolution, 12 kilometers. Carefully selected GCMs were used as boundary conditions, and that way we showed consistency of the physical mechanisms responsible for the drying. And then we developed the framework for assimilation of satellite and model data to estimate snowpack over the Atlas and how that impacts runoff. So this is really a short summary of the situation with climate change impacts on water over the Mediterranean. And I would like to spend the rest of the time in this webinar talking about the Nile Basin. And that's a system that I have been, much more connected with. I have actually we published our third book on the Nile, and we're happy to share some of those results with you. However, I would like to start by saying that climate change is not a new phenomenon on the Nile Basin. Climate change did happen thousands of years ago over this area. These are here evidence of paleoclimatic records of observations in caves in the middle of the Sahara where people found evidence for this picture. Like, for example, in this cave here in Libya, there is a picture of an elephant. And in another area in the Sahara, there is a picture of a giraffe and cows. These are animals that do not exist now. And by radiocarbon dating, these are reflections of past climate that happened in that region. But it's not only those pictured in the caves. There have been many studies, paleoclimatic studies, where people found evidence for more humid conditions during the Middle Holocene, like 6,000 years ago. And this evidence includes things like samples of soil, charcoal, human bones, large animals, fish, plant remains, widely spread over the desert area. If you put all these pieces together and try to reconstruct what happened, you find that about more than 9,000 years before. So to read this picture, here, this is Siwa Oasis, so this is about 30 degrees north, and it goes down to about 16 degrees north, Wadi Huwar in northern Sudan. So this is the area between, you could think of the area between Cairo and Khartoum. That's the north direction. And then in time, we are going back on time 3,000 up to 9,000 years ago. And you see, before 9,000 years ago, this area used to be very dry. And then there was a period of significant wetting, greener area. And that's, each point here represents like some evidence that had been interpreted, including, earliest proofs of cattle, goats, sheep, graves, all kinds of animals. So this is an interpretation of the past. And then about 6,000 years ago, another drying period started. That's, ended like, about 3,000 years ago or so. And that's so climate has changed in the past over this area, 6,000 years ago and before that. And the way people adapted to that climate is shown here in evidence of human settlements. Like 10,000 years ago, people were settled on the Nile Valley. During the wet period, the population spread in the desert because it was wetter and greener. And then about 6,000 to 3,000 years ago, people moved back to the Nile Valley. And if you look at that, consistent with archaeological sites, archaeological history, that climate change coincided with the emergence of the pharaonic civilization. So the climate change from wetting to drying, where people moved to live on the valleys of the Nile, coincided with the emergence of the pharaonic civilization. And this is here a picture of my favorite pharaoh, Akhenaten, his wife, Nefertiti, and their children. And even their god Aton here, the god of the sun. And this, Akhenaten is a very significant, pharaoh for many reasons. He was revolutionary. He introduced monotheism and moved his capital to Tel al-Amarna, and he did a lot of things. He's a very significant guy. I have to say that his mother, Tai, there is a theory that she is originated from Nubia. You see, that's actually in archaeological evidence. There is always like debate about things. Things are not clear cut and not, but Tai is the mother of Akhenaten, and that's her picture there. So what caused this climate change that happened thousands of years ago? What is the cause of it? It wasn't because people were driving cars and like emitting CO2. It had to do with changes in the solar orbital parameters. For our time scale of years, tens of years, hundreds of years, we could assume that the orbits of the sun are, constant in terms of like how the Earth rotates around the sun, the obliquity, and the precision. So these are parameters that describe how the solar Earth system works, but at time scales of thousands of years, those parameters do change. And when they change, the solar radiation change. And when that solar radiation changes, the climate changes. So this is a climate change that happened thousands of years ago. It wasn't due to the CO2 emissions. It was due to the changes in the solar orbital parameters. And we have done studies in my group in which we tried to simulate that using our models, to test our models to simulate that thousands of year climate, how it happened. Here again, this is my favorite picture of the rhodanilometer. This is a picture by David Roberts in 1850, where he came to visit Cairo, and then he saw the rhodanilometer, and you see that there is this pole there that's gauged, and these gentlemen, they come down and they measure the level of water, and that's really quite a nice picture, a nice drawing. Nobody would do that now because everyone had an iPhone, and they would if they see something they like, they just take a picture of it. That's a lazy way of doing it. So the nilometer record, however, I described it in one of my papers as the longest human record of a geophysical phenomenon. It's about 1,000 years, and you see a picture of it over there, and it's really an indication for how the importance of the Nile for life on this valley. People monitored and they kept records of the Nile, and I have used it actually on one of my research papers. I used this record in one of the papers we published. And for the people who are not as, not for this audience here, people are very familiar with the Nile. But I like when to describe the Nile, I like to use the unit that had first been used by Hearst. Hearst was the engineer who designed the highest one dam. And he talked about a 12 cubic kilometer at his unit. His unit is 12 cubic kilometers. So if you have 7 units, so 2 units of come from Uganda into South Sudan. 1 unit comes from Ethiopia through Sobat, and 1 unit gets lost in South Sudan. So you get in the White Nile 2 units, and then the Blue Nile gives you 4 units, each of them 12 cubic kilometer. Adbara River gives you 1 unit. Another result, you get, 4 plus 2 is 6, 6 plus 1 is 7, and that's the long-term record in Aswan is about 84 cubic kilometers, more or less. But just for the non-familiar with the hydrology of the Nile, this is the big picture. Where does the water come from, how it flows, which river systems, and so on. And of course, we all know that the Nile has been, is a very important river. Fluctuation in the Nile floods have been of importance to the people in this part of the world. And it even came in stories in the Bible and the Quran, the 7 years of plenty followed by 7 years of shortages. If anything, even for the non-believers, it's an indication for how the river was an important, for the people who live in this area. And there is also, speculations, archaeological speculation that this guy, Amenhotep III, was maybe the pharaoh during the time of Joseph, during those periods. But that's not known. This is not scientific knowledge because in archaeology we don't have the evidence and we don't have the observation. But this is just a speculation. But Amenhotep III was resigned on a period in which unprecedented prosperity, cultural and international power. He was really quite a significant pharaoh. So what caused this year-to-year fluctuation of the Nile flood? We know that, the Nile basically, you have the high seasonality. This is how the seasonality, where it comes from, the Blue Nile, the River Adbara, the White Nile. And however, there is significant fluctuation that happens from year to year. The source of this data that I'm presenting on the right was Dr. Abu Zaid in this was when I first went to MIT in 1992. I wanted to study the Nile. My advisor, Professor Brass, gave me his number and he said, oh, you contact Dr. Abu Zaid and he's the person. So he sent me this data, and all the work that I did on the Nile and El Nino would not have been possible without that data being shared generously by him at that point. But I want to show you, so this is basically a century of data from 1870 to 1970 and how the Nile fluctuates. What I would like to draw people's attention to is if you look at these 4 years here that happened, towards the second half of the 19th century and early 20th century. Look at these 4 years. These 4 years are quite remarkable in being dry years. I'm pointing them here. Dry years. Each and every one of those 4 years was an El Nino year. El Nino, I'm going to talk about El Nino now, but it's clearly, you look here, and these years do stand out. It stand out as significantly below average flows, and all of them were El Nino years. So we use this same data, and in 1996, we discovered the relationship between El Nino and the Nile flood, such that when the sea surface temperature in the Pacific Ocean is warm, you have low flow. When the sea surface temperature in the Pacific Ocean is cold, you have high flow. We call that La Nina, El Nino and La Nina. And so that's why when I published this book recently about natural variability of the Nile floods, I call it From the Pharaoh's Dream to El Nino, La Nina. So that's, from that time to our time, that's what this variability is about. And so let me share with you here this video about what's El Nino. Okay, so yeah, I think this is not going to work because of the yeah.
seasons for different regions, even raising global temperatures. But what is El Nino and how does it happen? Firstly, we need to know what's normally happening in the tropics.
Yeah, I think. Just a second. So I think we are going to. Oh, I'm muted. So mute me again. So sorry about that, but that's video based. So that video was supposed to. No, the voice.
Okay.
Yeah. So that video was supposed to show the give information about the Nino, and it's basically a phenomenon that happens in the Pacific Ocean every few years. The temperature of the Pacific Ocean will get warmer than usual, and when that happens, it has impact on weather and climate around the world. So it's really a connection between the weather and climate around the world and the conditions in the Pacific Ocean, and it has been studied significantly by many groups around the world. So now let's get closer to look at situation on the Nile. And I would like to talk about the Nile, and I always describe it as a microcosm for Africa. The Nile, if you think about it, the Nile Basin is like an example of Africa. It's a microcosm for Africa where there is urgent needs for sustainable development. And to describe that sustainable development, I developed this equation. I invented this equation, which I call the equation of the future of Africa. You know, it's not a serious equation, but it's useful to think about the conditions. I call it the equation of the future of Africa, where C is like economic output. And I say it's function of water, W is water, T is technology, and P is population. So you could think of economic output, you could think of like agricultural output per person is basically how much water, but just having water is not enough. How do you use the water? How smart you are about using the water? That's T, the technology. And then P is really output per person. It has to be per person. You can't just think of large scale. So if you take equation 1 and you do like simple calculus on it, you take the natural log and then you take the derivative, which is very simple calculus. We tell people that MIT professors are not allowed to give a lecture without showing one equation. So this is my equation for today. So it's a very simple equation. So you take the derivative and you end up with these 4 terms, which I really like, and that's why I emphasize it. Economic growth, this is the relative change in economic output, d ln C by dt, is d ln W by dt, which means the fractional change in water. That's climate change. Climate change changes water availability. The fractional change in T, that's technology adoption. That's basically, and here is agricultural technology. And then population, d ln P by dt, that's the rate of change of the population. And what I love about this equation is that naturally population comes up with a negative sign. It's the only thing there that comes up with a negative sign. So the change in population is a negative process. It's not a positive process. So this equation provides a framework for us to discuss these issues. And so let's talk about technology adoption. What do I mean by technology adoption? So technology adoption is agricultural technology, which means the agricultural efficiency, which is a function of 2 things, the water use efficiency and the crop productivity. The water use efficiency and the crop productivity. So how smart about using water, and then how much do you produce out of that water, okay? And so if you think of that, you look at Africa, and this is actually, I find this puzzle, it's quite surprising. How much irrigation in Africa? The irrigated area in Africa is currently amounts to only 30% of the potential area. The largest irrigation is in the delta. You see, look at the whole map of Africa. The only area where it's red is the delta, and then the Nile Valley in Egypt, and then you have to come down to the Jazeera scheme in Sudan. And you look at other parts of Africa, very little irrigation has been developed. The intensity of irrigation is very low. So that's what I mean by technology. Irrigation is a technology to be more productive with water. The other emphasis I make here, and this is very interesting, this is how much fertilizer use. People use fertilizers, and how much the cereal yield, the yield in terms of agricultural output as a function of fertilizer use. This is done by Professor Tillman from Minnesota, and he tells me that these least developed countries, these are African countries. So in Africa, we use very little fertilizers, and our productivity is very low. And these countries, developing countries, this is like, Europe and North America, and now Asia, China, and India, they all figured out this, and they are producing more. So you look at here, this is the map of use of agriculture. Look at Europe. Europe is almost yellow. The whole of it is yellow. North America, look at North America here, very high rates of application of fertilizers. Africa, you have to really look very hard to find out where it's being applied. India and China, they had their green revolutions. India and China now are very productive. They use a lot of fertilizers too. Africa is lagging the world in that dimension. As you see here, you could see here the delta of Egypt. There is some use. Egypt had been more advanced in this area compared to other African countries, and they have been more use of that. So if you think of this picture now, this is now here more detailed. Sudan, Ethiopia, and Egypt as countries in the Nile Basin. You see Sudan had been using very little fertilizers, producing very little yield. Egypt, however, has been using a lot of fertilizers, and it has been quite productive. Agriculture in Egypt has been quite productive. Ethiopia has recently started using more fertilizers, as indicated in this figure here. You see the progress that was made in Egypt in the 1960s, 70s, and into the 1980s and 90s. It really doubled, or maybe even more than that, doubled to triple the use of fertilizers. Ethiopia have figured out this technology recently, and they have been applying more. And Sudan, unfortunately, is lagging. I have had started recently, before this war in Sudan, I started a project that tends to focus on this problem, is how to get Sudan to really invest in fertilizer. So if you think about it now, this is a lecture about water. What fertilizer has to do with it? It has to do a lot with it, because if you want to increase production, you could increase production by using more water, or you could increase production by using more technology and fertilizers. And if you do that, you may need less water. So if we are in a situation in the Nile Basin where we have, conflict on water, too little water, one way for us to move forward is to expand the use of these technologies, and so that people do not need to use as much water, and the water would be enough for everyone. So now let me move to the second topic, which I really think is a very important topic. So this is again my equation of the future of Africa. You see, so in one hand, we have to green Africa. The other is we have to think of
Faleh equation.
Yeah.
This is the Faleh equation.
Fatih equation. So here look at the picture of the population, and this is I think is a big problem in Africa. I think this is the biggest problem facing Africa. Let me tell it this way. The world is expected to add 2 billion people by 2050. 2 billion. One of those two is going to be in Africa. A continent that has now about 1 billion, the population of Africa is going to double by 2050. The continent that has the least capacity to absorb population is going to be responsible for half of the change in population in the future. And so that's why I emphasize this population as a big problem. And it comes naturally from that equation. Here, this is the population for the Eastern Nile, Egypt, Ethiopia, and Sudan. Until recently, I think, if you look 2020 or so, the population was more like, 250 or something like that. And it's projected to go to close to 400. Mainly, so these increases in population are quite a serious problem, I think, facing the basin. And this is here something I usually make a small joke here that the population problem is not a new one. You could even this picture with Akhenaton, he has 3 children. And I read in somewhere that he had 6 of them. So that's close to the fertility rate that we have now. So anyway, that's a side issue. It's an African problem. I don't mean by showing the pharaohs that it's not an. Actually, I documented in a recent paper that Egypt has made progress in this area. It's an issue where the government has the right priorities and it made significant progress. And so now Egypt is doing better than other African countries on this regard. And so, however, if you look at the projected increase toward the end of the century, and then convert that into water availability per capita, you find that if these tracks of population increase are followed, that all these 3 countries, Ethiopia, Egypt, and Sudan, will all be below the absolute water scarcity index. You see, even Ethiopia, which is supposedly a rich, a country that's rich in terms of water resources, if it continued in the current track for the increase in population, toward the end of the century, they would have absolute water scarcity. So population is a significant problem. That's the message I would like to convey. And it has the most effective way to address population in Africa is through education of girls in secondary schools. So basically expand the education of girls in the secondary schools, and there is a significant correlation between the total fertility rate and how much percentage of girls enrolled in secondary school. That's the way forward for that problem. So now, having covered the context, I tell people climate change doesn't happen in a vacuum. It's not like there is no other problem facing the world and then just climate change is the only thing. There is a set of issues that are facing the world. In Africa, it's like, fertilizer, agriculture, population. And then on top of that, climate change is happening. So let's look at what climate change is going to impact. So this is data here I'm going to show. This is data for the Atbara River and for the Upper Blue Nile. This is the best data that's available. And we did analysis looking at the observations. And if you look at the moving average of the standard deviation and the average flow, you see that recently there have been statistically significant increases in the flow of the Atbara River and the Blue Nile. There have been statistically significant increases of a small magnitude. That's just what the observations are showing. So the mean flow for Atbara increased by about 17%. For the Upper Blue Nile increased by about 10% during this period. This work, by the way, comes from a Nature paper by myself and a former student of mine, Muhammad Siam, who is originally from Egypt. And so that's what his PhD thesis. So we also looked at the standard deviation. The standard deviation, however, increased by 40% for the Atbara River and 25% for the Upper Blue Nile. So the changes in the standard deviation are larger than the changes in the mean. And so that's, the ratio of the standard deviation to the mean, the ratio of the standard deviation to the mean in statistics, we call it the coefficient of variation, So that coefficient of variation for the Nile actually mimics in the record, this is the observed record of the Nile, it mimics the number of La Nina and El Nino years. So the variability from year to year in the Nile floods relate to the concept of the El Nino that I talked about earlier. about that correlation. So there have been studies recently, these are papers published in Nature, not by my group, by other people, that there will be an increasing frequency of extreme El Nino events due to this greenhouse warming. There will be an increasing frequency of extreme La Nina events under greenhouse warming. So the models are saying that we'll have more of these El Nino and La Nina in the future. And so when you look at then all the GCMs and what they are projecting into the future, you see that the models are showing an increase in the mean flow by about 15%, but an increase in the standard deviation by about 50%. So this draws a picture where in the future, we are going to have, more water, which is good news, especially when you compare it to what we have discussed related to the what we have discussed related to the to the Mediterranean. And however, so we are going to have more of this, but this water is going to come with fluctuations from year to year. So the coefficient of variation of the Nile flow in the future is like the coefficient of variation is likely to increase in the future together with an increase in the number of El Nino and La Nina years. So together with an increase in the number of El Nino and La Nina years, there is a projection that the coefficient of variation is going to change. So now, if we take this information and basically look at the Hertz equation, which is an equation that showed the storage that's needed in a certain system to meet the flow in a certain number of years, you could see that. Oh, what happened there? Yes. So what's happening is that you see how in the past, this is the relationship between the storage. Yeah, this is the relationship between the storage and because of the increase in the standard deviation and increase in the flow, the amount of storage that need to basically satisfy the average flow for a certain number of years. For example, if we think of what you need now to have, if you think of what you need to have the average flow for a return period of 60 years, you see that the storage needed is about 250 cubic kilometers. In the future, that storage, however, will only give you the average flow with a return period about 40 years. So if you want to have the same conditions at the 60 years, you may need to increase the storage to about 350 cubic kilometers. So the idea is like, if you have a system, this is just general statistics, if you have a system where the fluctuations are wilder, meaning that there has to be more high floods and low floods fluctuating from year to year, it would be necessary to add storage in order to basically control that water, just in general. If you have a river that has a larger standard deviation than another river, you need to have more storage in order to meet those demands. Here, I would like to show you, this is the emphasis I made on the population. If you take the water per person and, for the base climate, taking care of the projected population, you see that the water per person would go from 400 cubic meters per person down to about 200. If you add the climate change, it improves the picture a little bit, but you still have a significant decline in the water per person. So what this really emphasizes is that the population growth in Africa and the population growth in the Nile Basin is a very significant problem. It's a more significant problem than climate change. It's more significant problem than any dam being built or anything. It is the problem that has to be addressed if you are going to have enough water for all these people, because the numbers that are coming up are quite huge. So here I have another video that actually I would like to share, but I don't know if it's going to work or we're going to have the same problem. So did we figure out how to? And then it starts. No.
Basin. Today,
main water artery for Eastern Africa, and for the 400 million people living along its shores, a vital resource. Unfortunately, the Nile Basin is. For millennia, people have relied on the fertile soils and constant flow of fresh water in the Nile River Basin. Today, this river fills water bottles, irrigates crops, and creates hydroelectricity. Climate change, however, threatens to disrupt the delicate balance between the Nile and the people it sustains. A recent prediction of climate models is an increased occurrence of the climate oscillation responsible for El Niño and La Niña. Now, scientists at MIT are suggesting this variability is also likely to be reflected in the flow of the Nile River, resulting in more frequent floods and droughts, especially in the eastern Nile region. With tributaries running through almost a dozen countries, the Nile River serves as the main water artery for Eastern Africa, and for the 400 million people living along its shores, a vital resource. Unfortunately, the Nile Basin is already an ecosystem under significant stress. So what will happen as climate change progresses? According to the recent study, it's not looking good. Considering climate model simulations of rainfall and stream flow, the research team projected future river flow patterns. Observational data were used to document recent trends, while global climate models were employed to estimate future runoff. These models use mathematical formulas that take into account greenhouse gas emissions and how they affect climate, allowing scientists to make future projections under the business-as-usual scenario of emission levels. From these data, a troubling trend emerged. The coming years and decades are likely to see an increase in the variability of river water levels, attributed to increases in future occurrences of El Niño and La Niña events. For people living in the Nile Basin and relying on the resources it provides, this translates into more frequent fluctuations manifested in extreme floods and droughts, the effects of which are already being felt. In 2015, regions along the Nile saw the worst drought in a half-century, causing crops to fail and food prices to skyrocket and leaving millions hungry. A year later, hundreds of thousands of people were displaced and houses destroyed by floods along the river's banks. Scenes such as these are likely to continue as climate change progresses, threatening environmental sustainability, local cultures, and food security in this already fragile region. With the population in the Nile River Basin expected to double by the year 2050, the demand for water is growing stronger every day. While the data suggest ongoing climate change will likely increase overall average water flow in the river, this additional water comes at a price. Increased interannual variability will require building dams to store water surplus during flood years for use in drought years, incurring both economic and environmental costs. This combination of projected population growth and climate change impacts presents the Nile Basin as a microcosm of Africa in the 21st century. The projected changes in Nile River flow predicted in this study highlight the need for careful future planning regarding the protection and utilization of this essential resource.
Okay, so in summary, for the future of the Nile Basin, the control, I think, of the rapid population growth is the #1 priority for Africa and for the Nile Basin. There is progress happening in some countries. More progress is needed. Investments in irrigation and agricultural technology, fertilizers, better seeds is a close second. In the Nile Basin, challenges of population growth, adoption of agricultural technology, and climate change are much more significant than those associated with any single dam. These are big problems. Adaptation to climate change will be needed in the future, so better plan for it now. And maybe it's about time to ignite Africa's green revolution. So that's basically it. Thank you very much.
Okay, thank you very much, Professor. Really, you took us back 10,000 years ago, and you link it very much with what the future will be to us, and the difficult time which perhaps would come if we are not really started to prepare ourselves in the Nile Basin and in Africa. I think I will give now the floor to Dr. Khalid Abu Zaid to give us some reflection, being himself also on the Nile and very drowned on the water aspects and problems, and to reflect also on the lecture itself.
Thank you very much, Abdeen, and I'd like to a very interesting presentation, a lot of information, very interesting findings. If I may comment and maybe raise some questions also on what was presented, hopefully Professor Al-Fateh can provide some insights on and clarifications that would be appreciated. From the maps that you showed on the Mediterranean at the beginning, you showed that there is going to be a decrease in the precipitation in the Mediterranean region. But I noticed also that in the Sudan area, for instance, it seems like the color was blue, showing that maybe it's going to be indicating an increase in the precipitation in that area. So maybe a clarification on this would be useful. Also, you mentioned that the fluctuation in the precipitation, but what about the total volume of rainfall within the Mediterranean? Is it going to be a total increase in volume? There is going to be an increase in droughts and an increase in these fluctuations in precipitation, of course, will need new ways of managing water to capture the highs and to use the storage during the droughts, of course. And these are parts of the adaptation to climate change that we're talking about. Also in the Mediterranean, where you showed that there will be a decrease in the precipitation, some areas within the Mediterranean, I saw some also blue. I think it was maybe the borders between Libya and Egypt where it showed some blue. Does this mean that parts of the Mediterranean coastal areas might see an increase in rainfall or precipitation? That's one of the questions. You also mentioned that there will be a decrease in the precipitation in the western part of the Mediterranean and in the eastern part of the Mediterranean. But we've noticed a lot of rainfall and flooding in Morocco and Sudan and Spain recently. And I mean, this may be followed by an extreme drought sometime in the following years. But if we add all the precipitation that caused this flooding in Morocco and Spain this year and last year, does this mean that the total volume of rainfall might still be increase, or it will still coincide with the findings that precipitation is going to increase? Because there were huge amounts of rainfall that really flooded these areas, Valencia and also some areas in Morocco. Another interesting observation that you mentioned about the solar orbital patterns, and that climate change may have been caused by this phenomena and not necessarily by emissions, because at that time there was less emissions, that maybe these solar orbital patterns have caused these long-term climate change. And the solar radiation changes and all that. How significantly is this going to also affect the future as compared to the increased emissions that everybody's focusing on, and the mitigation measures that need to be taken to reduce these emissions? On the other hand, you talked about the El Niño phenomena, and that is associated with the warming of the Pacific. Whereas I think the source of rainfall for the Nile Basin, for instance, may be coming from the Indian Ocean and not necessarily from the Pacific. Is the same phenomena happening also in the Indian Ocean, or is it just the Pacific that's causing this phenomena?
Maybe I will address this set of questions and then I could come back to you. So I could address this set of questions that you raised. Many of them are important ones. That I think the map that you are absolutely right. The map that you are showing, you are referring to. The general picture with climate change, that there's going to be more rain around the world, with few significant exceptions. And the most significant exception is the Mediterranean, the significant one. The area that you said will increase rainfall is true. That if I could show it if I could link again.
Yes, of course.
Can I link again the
presentation?
Yeah, the presentation again. Yeah, I think you are referring to this figure that you see here. Those large.
It was a focused one, a more.
Yeah, this one here.
Focusing on the Mediterranean itself.
There is one focused on the.
Zooming on the Mediterranean. Yes, the one above, the one on top.
Yeah, those are actually.
Blue area in Libya and Sudan and Egypt.
Yeah, this is the observed trends up to now. Exactly. This one is the observation.
Yes, exactly.
And you see, as you see, there isn't much changes in the coast of the Mediterranean, even in the models or in the observations in the southern coast. The most concentrated changes are southwestern Turkey. This region here, southwestern Turkey, and also the Morocco area. Yeah, this is a small change that in the observations we don't know how significant it is, and this is, I think, it's mostly between Libya, as you said, between Libya and Egypt.
Also in Algeria.
Yeah, the records here. If you look at the previous slide here. You see here, you mentioned that there is, this one here.
This is the projected.
Yeah, there is a delay. There is a delay. You see these changes that you see are, yeah, takes a while for it to, yeah. So for example, there is a big green over, Arabia and the Sahara Desert. Those are because these are percent changes. When you divide by a small number, you get a big number. Like if you get 5 millimeter increase over the Sahara Desert, that's maybe 100% increase in rainfall. You see what I mean? It's because the rainfall is very little to start with. If it's 5 millimeter and you get another 5 millimeter, then it turns out to be 100% increase. So those are explain that. Going back to your question about the orbital parameters. The orbital parameters do change, but they change over long time scales, thousands of years. So it's not something that we need to care. Climate change is happening at decadal time scale toward the end of the century. So decade to like 1 century. The orbital parameters, the solar forcing changes are going to happen, but those do happen at time scales of thousands of years and tens of thousands of years. So if you are interested in what's going to happen at those time scales, yes, those are significant processes. And that's what the paleoclimatic record was 6,000 years ago. Your question, you had a very good question about these extreme events, like the one that happened in Libya, that happened in Morocco, it happened in Spain. Yesterday, I talked about what happened in Arabia too. And yesterday, I was saying that although you may have an extreme precipitation increase, the average rainfall doesn't really change. You see what I mean? Because of the mechanisms are different. So you could have a situation where you get extreme precipitation, but it doesn't add up total. You see, it doesn't add up to the total because you may have, for example, in Arabia, you have less days with rainfall. When it rains, you get a lot, but you don't get as many days with rainfall. So the statistics then average out to no significant change.
Sure, but I think that
قبل ما الناس يكتبوا ابتدى نعمل اعلان حسام موجود؟ لا طلع؟ لا خلاص قاعد بدنا ناخذ صوره للناس لكن طلع صغير. حسام ما موجود، لا حسام ما موجود. Go ahead.
Yes, of course, but I think that you might agree with me that we need to be monitoring collecting and compiling the observation and measured data, because as you mentioned, that overall globally, the rainfall volume on Earth with climate change is going to increase.
Mm-hmm.
So, and it may happen in Spain. I think, work on the collected and observed data to prove one way or another what's going on, because this might lead us to looking at different adaptation measures. You mentioned increasing storage, for instance, to capture the highs and the lows and all that. So we may be looking at these as options in some areas. So look,
actually, that's
total volume. What's going to happen is and where is very important, I think.
Yeah, I think yesterday too, when we discussed Arabia, we suggested that these extreme storms, we may turn the curse into a blessing by capturing that water and using it. And actually, our project in Morocco advocates the same thing, advocates for capturing some of those big storms and storing the water and preventing evaporation. So there could be, ways to adapt by using this extreme storm that happened, and if we could find ways to store the water. I mean, in hydrology, we all know that, if you have variability, you have fluctuations, storage is a solution. The engineering solution is storage. You build a storage so that you could store the water from the time of plenty to the time of shortages. That's in general.
Other things you mentioned about the need to increase irrigation, or right now in Africa, the irrigation potential, we're just at 30% of the potential irrigation area in Africa. However, I would like to make a point here that because irrigation has also its impacts, if we're talking about irrigation on water from transboundary rivers, and to work on increasing or improving the rain-fed agriculture. I mean, because we could improve agriculture productivity by also improving rain-fed agriculture, and these are parts of the nature-based solutions that everybody is talking about now, and that wherever rain-fed agriculture is possible, we don't have to really enforce irrigated agriculture versus rain-fed agriculture, but ways of improving rain-fed agriculture through scheduling of agriculture practices and better agriculture practices and fertilizers and things that you rightly mentioned are or could be ways that have less impacts, especially on transboundary river basins. But in the meantime, they could improve agriculture productivity, not necessarily by just increasing irrigation area. There is a big potential. Africa, the sub-Saharan Africa, for instance, there's a lot of greenery in sub-Saharan Africa, and it's all rain-fed. Whereas whether it's rangeland or rain-fed agriculture areas or forests or other things where maybe rain-fed agriculture can make a difference there. You also mentioned that there is a decrease in water, an expected decrease in water availability due to the population increase, and you showed the indicator of the per capita renewable water resources for Egypt, Sudan, and Ethiopia. And I noticed there that these indicators, although the data may be coming from UN sources, but still what I noticed is that these indicators are talking about the blue water per capita share and is not taking into consideration the green water availability, especially in Ethiopia, for instance, where the per capita share, if you consider the water that goes to rain-fed agriculture and livestock production, through rainfall and rain-fed areas, the per capita share may be much more than what is shown there for, especially for Ethiopia, where it has a lot more green water than Egypt or Sudan. And this is something that I think we need to work on redefining the term or the indicator of renewable water resources. What do we mean by renewable water resources? Does it include only blue water, which is water that is surface water or abstracted groundwater, or should it also include water that contributes to rain-fed areas? The runoff that you showed also projected flows for the Upper Nile and the Adbara Nile basins, and the projected runoff. There is something that everybody is not considering when they look at future expected or predicted runoff, which is the urbanization that's taking place everywhere. And I think that if we take that into consideration, because as urbanization increases, the runoff will increase. The seepage and the groundwater percolation and all that will eventually decrease, and there will be more runoff in the future with expanding or expansion in urbanization. And this is something that I think we might want to consider in our future projections of expected runoff. Also, the recent flow data in the Nile. I mean, you've shown 4 low water flows or runoff for the Nile in the past. But what happened during the last? There is also maximums for the Nile flows as well that happened in the historical data that we have. But we need to analyze also what happened in the last 5 or 10 years, because some of this data may not be reflected in the data that we're looking at. And the impact of climate change recently on the recent flows and the recent runoff and recent precipitation need to enter into the equation. And I'm personally interested to see what are the recent data on runoff compared to the historical data that we have. Are those becoming less? Are those maximums that we have, are they becoming higher?
Yeah, but that's
measured data.
That's something I showed.
But I'm talking about the recent years, the very recent
Yeah,
years.
that's, if you carefully look at what we...
Yeah, that data, that graph that you showed on the fluctuation of flow.
Yeah, this is the flow data and how it's changing.
Yeah, see the last...
And this is the moving average. So this is the moving, this is exactly what you are asking for, which is how the recent flow compares to the past. And what is just showing is that this is the moving average. The moving average is increasing. So if you have a stationary time series, these lines will be horizontal, flat. The fact that they are going upward and going up beyond those dashed lines, that means statistically significant increases. Statistically significant increases of the flow. Just to address a couple of points you raised, because you have a long list. Urbanization increases runoff, and it could be addressed. It could be studied, and so that's no question about it. And also, you could estimate water scarcity based on rainwater and not only river flow water. I agree with that. However, I think you also have to, I showed something here very significant, which is the productivity of agriculture in these different countries. Egypt has, I think it's this year, this figure here. Look at where Egypt is, 7 tons per hectare. 7 tons per hectare. If you compare that to, this is really very high. I looked at that number. The productivity of cereal yield in Egypt is comparable to what's produced in the US. And the US is like the gold standard for agricultural productivity. If you ask the question, how that had been achieved in Egypt and not in other parts of the Africa, part of it is due to the use of fertilizers, as I explained. But a large part of it is because in Egypt you have irrigated agriculture. You have irrigated agriculture is much more productive than rain-fed agriculture. In fact, if the rain-fed agriculture, if the rain is sufficient, you don't need irrigation. That's what happened in the American Midwest. In the American Midwest, which is the most productive agricultural region in the world, you just depend on the rain. But the rain is reliable. It happens every year in sufficient amounts. And so you could rely on it. And agriculture is productive. In parts of Africa, and I know that this is an issue that has some sensitivity in the Nile and so on. When I talk about it, I'm talking about broad African perspective. For example, look at what's happening in. Let me show you the irrigation map. Look at what's happening in the Niger River Basin. Let's not just look at the Nile Basin. The Nile Basin, the issue of irrigation is a sensitive issue. But look at the Niger Basin. When I talk about irrigation needs to develop in Africa, there is nothing on the Niger Basin. You see there on West Africa, huge populations in places like Nigeria and so on, but there is no red area. The only red areas you see there is primarily in Egypt, in the Delta, and then in Sudan a little bit. And then, although in southern Mali, southern Niger, northern Nigeria, those are all areas where the Niger River, actually, it's very interesting what happened in the Niger River. The Niger River flows northwards towards the desert. And then Dr. Abu Zaid, the Niger River turns around and goes from the desert towards Nigeria, southern Nigeria. I tell people this is like water flowing from Los Angeles to San Francisco, or water flowing from Egypt down to Sudan. People wouldn't let that happen. The water, usually people let water flow from water-rich region to water-poor region. In the Niger River, after it goes through Niger, the water turns around and goes south. The river, I have seen it actually, I have been in Niger. The water flows from the desert down to Nigeria in the south. And I tell people that should not be allowed. That water should be captured and used for irrigation. So when I talk about the need for irrigation, is the need to incorporate this technology. Irrigation is an old technology. I mean, I'm saying this in Egypt. Egypt, like, thousands of years ago, people in Egypt and in Mesopotamia. So irrigation is a very old technology, and unfortunately, it hasn't been adopted enough in Africa. And that's the context in which I'm talking about it. Yeah.
That's because we often hear advocation for irrigated agriculture, whereas improving grain-fed agriculture through fertilizers or other practices could also achieve this higher productivity and higher crop yield. The wheat production in the States or in Canada are all rain-fed, and they have very good productivity. And I would like to add here also that whenever, especially in transboundary river basins where it exists, because irrigation upstream may affect water availability downstream in some river basins, that supplemental irrigation that may be needed in rain-fed areas could be from groundwater, where these impacts on the surface water may be less felt than depending in supplemental irrigation on just surface water, especially transboundary river basins. And I think that this groundwater is also important. And this brings me to the other point also that I wanted to mention, where you said that with the higher fluctuation in precipitation, we'll need bigger storage. And everybody now is talking about decommissioning dams and moving away from large dams and looking at nature-based solutions and things like that. And here I would like to highlight the importance of groundwater, using groundwater reservoirs as a natural storage reservoir, where in areas of rainfall, we should look at the groundwater aquifers as a natural reservoir for storage, and using this water in dry seasons, in years of drought, to pump it as a supplemental source of water, either for irrigation or for other uses. Especially that when we consider larger storage, we should also take into consideration larger losses from evaporation and from seepage of these surface storages. So we should, maybe if we take this into consideration, we might find slightly different results that might not make all this storage available or not. It depends on the amount of losses, of course. But considering groundwater, I think is very important in the equation. Thank you very much.
Yeah, thank
Storage that's needed is more like the highest one dam. The highest one dam, people wrote about, social impacts and environmental impact. I think in my view, the net effect was positive, and it's now, did work during periods of droughts in the 1980s. The idea that we emphasize here is that if you have fluctuations interannual fluctuations, you need to have system that could handle interannual water storage in an abstract concept. I mean, that's just being true to our like rooting in engineering hydrology. You know, like if you have that kind of need. Rain-fed agriculture, I'm pretty sure, you know, where rain-fed agriculture doesn't need advocates. I tell you, when it works, it dominates. And that's what's happening. The examples you gave in like the American Midwest and in Canada and elsewhere, because it's cheaper, it's more it's more profitable. So rain-fed agriculture, when it works, you don't need to tell people to go for it. We know that, for example, in Sudan, you know, Gadarif area, you know, is a rain-fed area. It receives significant, reliable rainfall, very profitable agriculture. And if tomorrow, like agriculture in Sudan, I think even now, if I would say during this war, there is rain-fed agriculture going on in Gadarif because of the profitability. The American Midwest is very profitable, but you need to have patterns of rainfall that are reliable, consistent, and so on. When you don't have that, and there is needs for supplemental irrigation, then irrigation technology, Dr. Khalid, is a very old technology. I'm saying this, I'm sitting here in Egypt and I'm saying this. The Egyptians practiced this like thousands of years ago. In Iraq, it had been practiced thousands of years ago for good reasons when it's needed. But I agree with you. Rain-fed agriculture could be made more profitable by use of fertilizers, and that's what Ethiopia started to do. And I think pushing them in that direction is good for everyone. That they could produce more because you may find it even more profitable to do things that way. Like you produce more from the same water. It's better than expanding, because when you expand, you don't only need water, you need land too. And you destroy the environment. So especially in Africa, you would need to use land and you will need to remove the forest and the other ecosystems. And that's all has negative impacts. But it's a very important point that you raised, and I mostly agree with you.
I would like to add one little.
Don't end. We want to hear to the other people.
Of course. But just one clarification on this. The reason why I'm saying that is that in Africa, if you look at the Africa Water Vision, for instance, they are putting targets to increase irrigation by 50%. So each country is trying to increase irrigation by 50%, regardless of whether it's better for them to have rain-fed agriculture or improve rain-fed agriculture or others. That's why I was raising it.
For it. That's why I mentioned the example of the Niger River Basin. You know, there are niches in Africa where you need it. There are areas that receive actually more precipitation than what rain-fed agriculture would be successful. Like, you know, it's a long topic. We could talk about.
Okay. Thank you very much, Dr. Khalid. And so now we would like the colleagues in the online, if you can put the camera on, we'd like to take a picture. Then we'll come back to you with questions really for, could everybody put the camera on to take a picture for the participant? This is good for us for follow-up in future and for, yes, please all of you open the cameras for pictures. Okay. Okay. It seems some their names there, but they did not open the cameras. Maybe the cameras are not working or something, or.
Oh, pajama.
Okay. Now it's all right, Tariq, or you need it more to give them more time?
The names are there.
The names are there, so we can take the picture now. Okay, then we move. I mean, we thank really very much Dr. Fatih and Dr. Khalid really for opening this very additional discussions beyond climate change, which is very good. All those things are really connected, I mean, to water and to climate change, which is the main issue of this webinar, but it is linked with all those other issues which are mentioned. Now we open the floor for discussion and comments from you guys who are outside there. And we will start as usual with Professor Ala. The floor is yours. Go ahead. Dr. Ala, you are there?
Yes, thank you very much, Dr. Professor Al-Fatih, for valuable presentation. You are mentioned already. I earned a lot of information, valuable information. Yes, sir, about you mentioned as for the climate in the Mediterranean Sea, especially in Egypt, you mentioned hot, dry summer, warm, rainy winter. This is climate, yes, I agree with you. But if the hot, dry summer, it changes to cold, wet summer, in this case, we can call the climate is completely changed. But in fact, it is still hot, dry summer because already we face some hot waves. As these waves may be extended for 2 days, for 3 days, 1 week, and so on. So also in warm, rainy winter, I think Egypt received a lot of sunrise hours, and the rain is fluctuated in the north. In this case, already we can say the climate is still fixed, no change. So I will give you example. Many believe that with arrival of autumn, such you are living right now, the temperature drops, yes. But what drops is minimum temperature should be going to at night. While during the day, the first half of the autumn tends towards summer, and sometimes severe heat waves occur and are combined by heavy thunderstorm that causes flood in the mountain valley, which may be due to climate variability. This is first one. The second one, if you please, as you know, climate change refers to long-term alternation of temperature and the typical weather pattern in a place, and the time scale occurs over decades, centuries, or even millions of years, while climate variability refers to in climate parameters such as temperature and precipitation that happen over short period, and time scale can happen over months, years, or even decades. So we have the time scale is completely different between the climate change and the climate variability. Yesterday, Professor Fatih, your presentation doesn't show to me the difference or crystal clear difference between climate change and the climate variability, extreme waves and flooding. As you mentioned, I think it may be due to climate variability rather than climate change. According to the term of climate change and the climate variability I mentioned, do you think climate change express climate variability? This is the second one. As for last one, as for sea level rise, not also climate change causes sea level rise, but in fact we have also natural geological process for the Nile Delta in Egypt For example, short-line retreat studies have shown that the short line of the Nile Delta is retreating at varying rates. This rate is partially due to sea level rise, which has been recorded at approximately from 2 to 2.4 millimeter per year, based on a tide data from Alexandria and Port Said. As the second one is due to subsidence. The Nile Delta region is also experiencing local subsidence, which exacerbate the effect of sea level rise. This subsidence is caused by normal geographical process and human activities such as groundwater extraction. Thank you, sir.
Thank you. Please
respond. Thank you, Dr. Ala. The distinction between climate variability and climate change is important. So climate variability refers to like the fluctuation that we are used to in the past between summer and winter, between wet year and dry year. That's climate variability. What we have been talking about yesterday and today are changes in the pattern of climate variability itself. When we talk about the extremes, like yesterday we talked about extreme heat and extreme flooding, those are measures of the variability of the climate of the past. And what we argued is those measures of variability are changing in themselves. And today, when we talk about the Nile, and we say that, you know, you're going to have this, we are not saying just the mean is going to change, the average is going to change, which is good news actually. It's good news that the average is going to increase, and it has been increasing. The average flow of the Nile has increased and it's going to increase. That's good news. However, the caveat is that the interannual variability, which has been of interest to people who lived on the valleys for like hundreds and thousands of years, that pattern of variability is going to change, measured by the standard deviation, measured by the coefficient of variations. So you are going to hear more of years in which, oh, we have too high flow, and years in which we have too low flow. That's what the models are projecting. And if we keep our storage system the way we have now, you may get years in which you have a lot of flow and our reservoirs are full and there is more water but we cannot handle. And then you are going to have years in which the flow is too low and we don't have water enough in storage to handle it. And so the idea that is you need to think of long term, this is not a short term issue, but you need to start entertaining the idea at the system, do we need to have more storage? And I think the experience of the highest one dam and how it functioned in the past, providing interannual storage from years to years, is something that we could learn from. It's a similar concept that it saved water from years of high flow to years of low flow.
Thank you. Any question from the colleagues in the other side, from the online? Yes, Ahmed?
Ashraf.
Ashraf, oh, Dr. Ashraf. Yes, the floor is yours, Dr. Ashraf.
السلام عليكم ورحمة الله.
عليكم السلام.
Thanks again for the nice talks and the discussions between both Dr. Khalid and Dr. Al-Fatah. It was very nice and fruitful. Actually, my question is about the. I have a few questions, if you allow me. The first thing is about the climate change over the Mediterranean and the. Is it that the fact that the Hadley cell is shifting a little bit to the north? I mean the results that you showed us is showing a high pressure over the Mediterranean, resulting from the global circulation Hadley cell shift, or what is the reason for that? If you could comment on that, Professor Fatah. The other thing is about the MIT regional climate model. Is it applied over many regions or only on the North African region? And where we can we find that results if it's available for public? So a few of our students actually working in the same area and may find it useful for them to use. Other thing, and this is the last question or comment. I have been reading a couple of papers, actually, or manuscripts about the climate model over the Nile Basin, and it is showing a high standard deviation, yes, but only in the dry season, and with almost the wet season with almost no change in the average, and very, very limited standard deviation within the wet season. So that makes that the total precipitation change is not that much, is not that high. So I don't know if this come along with the results of the studies that you have made in the MIT or not, but I will be glad to hear a comment from your side as well. Thanks, and sorry for the long questions. Thank you.
Yeah, thank you, Dr. Ashraf, for thank you for this question. Your first question is a very good one, and I did not get into the details of the mechanism on how the Mediterranean, because I think the details are too technical for this group. But what happens is you have a change in the latitudinal temperature gradient in the tropopause. And because of that change in the latitudinal temperature distribution, you get an intensification of the jet. And as you know, when the jet intensifies, that changes the patterns of the stationary waves at that level. So it happens that those changes in the stationary waves are such that the air above the Mediterranean becomes an area with high pressure. And that gets transmitted to the surface, resulting in the high pressure at the surface. On the other hand, because the water warms slower than land, that's an anomalous cooling of the Mediterranean that also creates a high pressure. Both of those factors add together to basically cause the decline in rainfall. So it's not a change in the position of the Hadley cell. It's an imposed change because of the changes that I described from above and from below. Regarding the MRCM has been applied in many regions around the world. And if you go in my website, eltahere.mit.edu, there is records of all the studies that we did, all the papers that we published, and you could find references there that could be useful. Thank you.
Okay. Thank you. Thank you. Any other question from the colleagues in the online part or in the في أي سؤال ستيفن في داخل الشات بوكس؟
أنا عندي بس
جايك أنت ودكتور محمود لازم يتكلموا في النهاية.
دكتور محمود ممكن يختم بقى، لكن أنا I'd like to thank Professor Faleh and Dr. Khalid for this information and this discussion and the intervention from our distinguished participants, Ashraf and the others. Now we spoke about what's the climate, the potential impact of the climate in Mediterranean, in the Nile, and so on, all of these. But now what I ask now is how we can, we are going to make some enhancement for cooperation in such type of improving and the application of such type models that they can work together, they can have adaptation strategies together, and so on. So what do you think, Professor, about how we can enhance this cooperation among the countries in the region? I have, there is a lot of challenges now about, especially you mentioned about the data sharing and so on, all of these types of.
That's a very good question.
Enhance this cooperation to come with then strategic adaptations for climate change impacts.
Yeah. If you think, this is a very good question, Dr. Hussein. I think that's.
What we have to do.
Yeah. Especially we are engineers and
we are witnessing now.
We are interested in helping society. So if you look at the equation I described, the equation of the future,
equation.
there are few things that we could agree on. I don't think a rational country would argue that an constrained increase in population is a good thing that they would like to maintain, and they will have the resources to be able to sustain development and growth with that increase in population. So I think cooperation around that, it seems to me, is a no-brainer. Otherwise, consequences are going to be serious, in my view. And it's beyond water, actually.
Yes.
Beyond water, you see these wars that erupt around Africa. Ongoing wars now, ongoing famines and so on. They are rooted in these environmental factors, I think, in my view. Another factor that I talked about agricultural technology. I keep talking about fertilizer. I did not used to do that in the past. I think I'm a hydrologist. I'm interested in water. What does water have to? Fertilizers is supposedly for agriculture scientists, in agricultural sciences. But it's very critical in the water domain because it determines the demand on water. We hydrologists tend to focus on the supply of water, but the demand is also important. And if you don't use technology efficiently, then you demand more water. And then that results in a problem. And so there is room, I think, for cooperation on agricultural technology. Egypt is a leader, I think, in Africa, in this area. It could play a role in this to the benefit of all. It could play a role not just for the benefit of all, because Egypt has interest in reducing demand on water upstream. There is a vital interest in doing that. I mean, Egypt had interest in either increasing supply of water upstream or reducing demand. Supply of water has to do with climate change, has to do with what we just discussed on that, and there is going to be more water. On the other hand, demand on water could be controlled and modulated through this. And then there is the effects of climate change, where we're saying, okay, there's going to be need for more storage. That storage has to be planned cooperatively. It's water for all. It's not necessarily in a specific country or another. It has to be, and it's not like the storage projects that are causing now controversy in the region. We are talking about more like the highest one dam, which is to store water from if I remember right, the time scale of the highest one dam was about 4 years, right? The early studies of HERS, in that time scale. It's not just from one season to another, or it has a longer time scale in it. So those are, I think, rooms for people to cooperate in moving forward. I think the future of Africa is going to be shared. Even now, countries like the US and Europe are, complaining about migration. Although there are seas, between Africa and Europe, but still people find ways to get there. Egypt is part of the African continent, so I think the future is shared, and so we have to find ways to collaborate, to cooperate, but it has to be for the benefit of all. It cannot be done with any selfish, attitude or maximizing benefits of one country versus another. You have to think of it. And I have written a book on this. I shared a copy with Dr. Abu Zaid, in which I come up with concrete proposals on how that win-win situations, not only one situation, could be developed. It needs change from all sides, in my view. I think all sides, there has to be a mentality change in all, but it's feasible. It's feasible to craft that and to move forward. So there is room for cooperation, I think. And in what I discussed, you may find some food for thought for that.
Okay, Dr. Mahmoud, you'd like to give few words? Please, somebody a question? Are there any question?
Chat box.
There are some?
Oh.
Please go ahead.
From Iman, if we superimpose these projections on the situation with other seasonal streams nearby the Nile, such as in other Sudan seasonal streams? Would you advise increasing storage in Darfur, Gash, etc.?
Yeah, I think this is a good question. You know, the rainfall in Sudan also is related to ENSO, and we have been talking. We have done studies on how climate change could impact rainfall in Sudan. There are needs to improve storage of water in different regions of Sudan. In the past, there have been more like efforts in like Hayat Tawfir al-Miyah and so on in storing water in Darfur and other regions. So I think having that limited small scale storage is always helpful.
Any other question?
Yes. I believe Africa needs to invest more on water harvesting for supplementary irrigation or rain-fed agriculture, as what is notices is the change in the distribution of the seasonal rainfall rather than the reduction in the average annual.
Yeah, I think there have been slight seasonal shifts in the rainfall. Water harvesting, the project we have in Morocco actually emphasizes water harvesting. This is a new type of water harvesting where we don't build storage over the surface, over the ground. We, at significant cost, advocate storing water under the ground. You know, basically building concrete storage to channel the water and then use it, have it all recovered. There have been efforts, Dr. Abdin mentioned about work in Saudi Arabia, Dr. What's his name? Dr. Walid Abdurrahman. Yeah. Dr. Walid Abdurrahman mentioned the studies in Saudi Arabia. So there have been efforts in the region. And we have been advocating water harvesting in Morocco as a mechanism for adaptation. And we think that it has a lot of potential, especially in reducing evaporation compared to other potential approaches. What other questions?
Last question from Dr. Nadia. My question about the hydropower projects that Ethiopia and Sudan have been planned and the expectation for the operation and generation in these considering.
Yeah, I think I talked about the Nile for like a couple of hours and I avoided talking about hydropower projects. So I think, okay, I could say this. I honestly believe that the problems that I raised, population in particular, and fertilizer, are more significant problems than all what's really on the surface, considering the Nile. I firmly believe that not only the Nile Basin, but the whole African continent, if we do not address the rapid increase in population, the future of Africa will be very bleak. And this is something that's not controversial. I have documented in my paper that in Nature Communications, this country, Egypt, has been committed for that objective for some time with some success. More needs to be done, and more needs to be done in other African countries. Because a continent that has the least capacity to sustain additional people, the continent that has least capacity, is going to be responsible for 50% of the increase in population of the world in the next 30 years. And the projections, by the way, of population, something very interesting about them, they are very accurate compared to the climate projections, compared to the economic projections. And that's because of a process which is very interesting called the population momentum. The population momentum refers to the idea that if you have already the children that have already been born in Africa, they are going to be there, they are going to grow up, and they are going to have children. And so that's built into the system. And that's why projecting population into the next 30 years is a very it's relatively much more accurate than my model that projects the climate for the next 30 years. And my model is much better than the economic models that they use by some of these economists.
Okay. Thank you very much, Dr. Fatih. I think really we have, but if we have a couple of words from Dr. Mahmoud, I think it would be good before we close the meeting. I mean, just a couple of words of wisdom.
أولاً
Should go.
بشكر شكر عظيم للسر فاتح على اليومين اللي فعلا أثرى فيهم معلوماتنا عن climate change والإمباكس على مناطق كثير في العالم، ومنها بالطبع الميديترينيان والنايل بيزن. وأشكر الدكتور عبدين على فرصة اتصال بالدكتور الفاتح وإقناعه بأنه معانا في اليومين دول، ونأمل إن شاء الله أن احنا نستفيد برضو بسيادته في المستقبل، لأن في موضوعات كتير حضرتك أثرتها محتاجة يعني احنا نتكلم فيها. باسم المجلس العربي للمياه، باسم البارتيسبانتس if I may، أقدم سيادتك بكل الشكر والتقدير على منحنا هذه الفرصة. وإن كان لي يعني تعليق بسيط يعني في النهاية، يعني احنا طبعا مسرورين للبيانات اللي حضرتك اديتها بالنسبة للنايل فيجن والمودلز، وفي الوقت اللي فيه الكونكلوجنز اللي يمكن حضرتك اتكلمت عنها، ان بعض المودلز دي بتوري ان في زياده في الرنوف. على ما اتذكر ان في بعض المودلز اوضحت ان في مناطق يزيد فيها المطر وبعضها يقل فيها المطر.
25% بلس قدام.
ده بيأكد لنا ان احنا نتعرف على كل ما هو داير في العلم يعني. وبالطبع التغيرات اللي حضرتك اتكلمت عنها في الاكستريمز اللي ممكن تحصل في بعض السنوات او المواسم، او الانخفاض الكبير اللي قد يحدث في تصرف النهر النيل الازرق. وكان الدكتور خالد تناول التصرفات في 100 سنة الماضية، وأوضح أنه هناك سنوات مرتفعة وسنوات منخفضة، إنما حضرتك بتسير برضه أن هذه الستريمز ممكن تكون أخطر من ذلك بكثير. وده بيؤكد أعتقد الضرورة للتعاون المطلوب ما بين مصر وأثيوبيا للتوصل إلى اتفاق، والسودان بالطبع، إلى اتفاق بيوضح كيفية إدارة النهر في ظل وجود السد الأثيوبي والسد العالي وخلافه. هذا يؤكد على أهمية الاستمرار في المفاوضات الدائرة التوصل إلى حل. طبعا حضرتك أثرت الأسباب الهامة اللي لابد التركيز عليها بالنسبة لمستقبل المياه في الميديترينيان والنايل بيزن، ومنها طبعا موضوع البوبيليشن والأمور الأخرى اللي حضرتك ذكرتها. فده كله يحتاج إلى دراسات إضافية ما بشك يعني. ففي النهاية أنا بشكر حضرتك على الفرصة العظيمة اللي اديتها لنا، وبشكر كل البارتيسيبانتس على وجودهم معنا في اليومين دول، ودكتور عابدين برضه من نتقدم لك الأكاديمية بكل شكر. طيب شكرا.
وانا برضه يعني بعتز جدا بالفرصه دي انه اخاطب المجموعه دي ومن خلالكم برضه الناس الاونلاين، واشكركم شكرا جزيلا للدعوه. وانا enjoyed enjoyed the presentation والinteractions و I look forward for future further interactions and collaborations ان شاء الله. شكرا جزيلا.
بس قبل اخر كلمه واحده من الاشياء طلبوها مننا يا بروفيسور فاتح من الناس الحاضرين دول، طلبوا انه نديهم نسخه من البرزنتيشن، تقدر ممكن عندك مانع وكده.
انا فعلا برسل لكم بي دي اف، برسل لكم بي دي افs منهم
جدا تو برزنتيشن. في شيء ثاني طلب نحن بنتكلم فيه.
الفيديوز I think you could share. الفيديوز you could share.
يعني انا
لكن
بفتكر
السلايدز and I will send PDFs version of it. Okay.
Thank you very much. I think we will do that. Thank you very much. في النهايه طبعا بيتكلم بالعربي. نشكركم جميعا. انا بفتكر يمكن حاجات طلعنا منها انه البرايورتيز اللي بركز عليها المجلس ومركز عليها الاكاديميه هي برايورتيز متداخله. احنا مع انه كان كلامنا هنا عن الكلايمت تشينج، لكن شعرنا بانه الكلايمت تشينج متدخل مع كل شيء، متدخل مع الكوبريشن، باعتبار انه الكوبريشن is more important and more essential and more important and more profitable in fact than conflicts. والمجلس برضه عشان كده الايشو بتاع الترانسبيرنت ووتر برضه ايشو مهم جدا، ويمكن الوتر دبلوماسي بعض يكون يمكن حضاره معانا ولا حاجه زي دي، فيبقى الاشياء دي متداخله. المويه بالنسبه لنا في الريجون ده is really a must. it's an issue. اي effort نعمله لكن بدون strong research و strong updating و strong work with the technology والاشياء instead of انا نستوردها نحاول نعملها نحن ourselves innovation. انا افتكر science technology and innovation is the way. ودي يمكن يكون المجلس في البرايورتيز بتاعته الخمسه اللي بيعمل فيها، والبرايورتيز برضه الاكاديميه ماشيه فيها للسنوات الجايه 6 سنوات دي. فنحن نشكركم جدا ونتمنى ان نتواصل وبالتواصل يمكن نصل ان شاء الله. شكرا جزيلا. شكرا للدكتور فاتح، بروفيسور فاتح، شكرا جزيلا. You have done an excellent job. شكرا للمعلقين دكتور محمود، دكتور حسين، دكتور خالد، دكتور وليد. نشكركم. نشكر الناس اللي سالوا اسئله او الناس اللي استمعوا وحضروا. شكرا جزيلا. سنحتفظ بالصور وباساميكم ونحن بنعتبركم نتورك، جزء من النتورك وجزء من التواصل. نفتكر الويبينار بيمشي لكن اهم حاجه عندنا النتورك which we established. عشان كده اللي ما رسلوا لنا منكم الديتيلز بتاعتهم نتمنى ان يرسلوها لنا مع
الفورمات
ان شاء الله. رسلنا لكم، احنا طلبنا فورمات بمعلومات اساسيه دي بتفيدنا حتى لو دارين نرسل لكم المعلومه ان فيوتشر عشان نرسل لكم. شكرا جزيلا وبارك الله فيكم. شكرا.